Welcome to Lecture 45, the first of a series in which we'll be dealing with this issue of the ether and the quandaries it poses for us, and then seeing how those get resolved. And then, at the end of that sequence, we'll also understand how the dilemma of Mercury's orbit fits into this whole picture. We'll be looking ultimately at Einstein's theories of relativity, but first we begin with a lecture in which we're just going to consider three things: the Earth, the ether, and light. The problem, as I suggested before, is that we can't detect Earth's motion relative to the ether. In this lecture, we want to explore that problem of how we try to detect Earth's motion. Before we do that, I want to ask a kind of obvious question. It's sort of obvious in hindsight. Here in the 21st century, even through most of the 20th century, anybody learning physics then might say, well, this ether, it was, after all, a very improbable substance. It had to be real stiff. It nevertheless had to be like jello, so it could propagate transverse waves. It had to propagate the waves very fast. It had to exert no resistance on the motions of the planets and stars. Very improbable substance, and we can't seem to detect Earth's motion through it, so let's just get rid of it. Well, if we get rid of it, dispensing with the ether, we've got to ask a question. What's the medium for light? In what kind of thing is light a disturbance? Remember where the ether came from. It came from Maxwell and others trying to mechanicize, if you will, electromagnetism, trying to give a mechanical explanation for electromagnetism. Electromagnetic waves would be waves in some medium. That was the ether. The electric and magnetic fields would be stresses and strains in that medium. The constants K and mu naught would be mathematical properties or physical properties described mathematically of that substance, the ether. So the ether did a lot for us. It allowed us to understand electromagnetism and electromagnetic waves like we would any kinds of mechanical waves. Absent the ether, we have to ask, what's the medium in which light propagates? Or, a slightly more pointed question, with respect to what does light go at speed c? Because if we have the ether, the answer is obvious. It goes at speed c with respect to the ether. If we don't have the ether, that answer to that question is not so obvious. Well, maybe it is obvious. Maybe it goes at speed c with respect to its source. But it doesn't. And I want to convince you of how we know that it doesn't go at speed c with respect to its source. That would be sort of the obvious thing. If there's no ether and I run at you carrying a flashlight, maybe the light is coming out of that flashlight at speed c with respect to the flashlight, and not necessarily, since I'm running relative to you, with respect to you. That turns out to be not correct. Let's take a look at a binary star system and see how that works. It turns out, by the way, that about half the stars in our galaxy are binary stars. That is, they are stars in which there are two stars in gravitational orbits around each other. And the particular binary star I'm going to start with today, let me bring it into existence, has a single massive star. It's going to be so massive, I'm going to imagine that it doesn't move much. Actually, the two stars would go around their mutual center of mass. But, okay, that star is sitting there fixed. And I've got a smaller star which is going around it in a nice circular orbit. So let's get that star started. There it goes, around and around in a nice circular orbit. And now here's the question. If light moved at speed c relative to its source, then when the star that's going around, the smaller star that's going around the bigger star, was moving toward you, the light would be coming to you relative to you faster than it would be when, half an orbit later, that star is moving away from you. And what does that mean? It means if you could actually see this binary star system moving, which you can't do, no astronomer can see a binary star system, at least one that's going around fast enough for us to see this effect. If you could see that binary star system, you would infer something that was very different from this nice circular orbit, because the light from the star, when it's coming toward you, would get to you much sooner, because it would be traveling a little bit faster, but it would be traveling across hundreds or thousands of light years of distance, and so that would make for a big change in how quickly that light got to you, and that would just mess up this whole picture of a nice, simple, circular orbit around that star. So the fact that we see a nice, simple orbit tells us that the speed of light is not determined by the speed of the source. Now, I just told you can't see these binary stars. but we can see them spectroscopically. We can see the light, the colors of the light given out by the stars, and the colors of those light are Doppler shifted, according to the Doppler shift that we studied in Lecture 18, the fact that when a source of waves is coming toward you, the frequency is higher. When it's going away, the frequency is lower. Those effects are real, and those effects we see, and those effects allow us to sort out that the object really is in a circular orbit, the one star around the other star, and that circular orbit is not messed up for us, or our perception of that circular orbit is not messed up by changes in the speed of light, depending on whether the star is coming toward us or going away from us. So binary star observations rule out the obvious answer to the question with respect to what does light go at speed c, answer being its source. That's not the answer. Light does not go at speed c relative to its source because the motion of a source relative to us doesn't affect the speed of light that we measure for the light coming from that source, and that's binary star observations are the perfect example that shows us that's the case, or that light is not going at speed c relative to its source. Okay, so what are some other possible explanations of the fact that we can't seem to detect Earth's motion through the ether? Well, maybe Earth is not moving through the ether. Maybe Earth is at rest relative to the ether. Well, if we believe Copernicus' idea that Earth is not in a special place in the universe, Earth is not at the center of things, that really violates the Copernican paradigm, something terrible. If Earth alone were at rest, it would be really, really very special. We know the other planets are moving relative to Earth. We know other stars are moving relative to Earth and relative to the sun. We're not at the center of things. We couldn't be at rest with respect to the ether and have nothing else at rest with respect to the ether. Maybe, on the other hand, the Earth drags the local ether in its vicinity with it. That would be okay, because Mars would drag its ether with it, and the sun would drag the ether around it with us. And everybody would measure the speed of light that was the same and didn't vary with position because the local ether would be being dragged along with you. The light would go through some funny acceleration as it went from one star's local ether to another's, for example. Maybe that happens. Well, it doesn't happen. It's ruled out by a phenomenon called the aberration of starlight, which has been known about for a long time. And the aberration of starlight works something like this. Here I've got a picture in which at the left you see the sun, the yellow circle. You see the Earth going around the sun in its approximately circular orbit. You see light coming in parallel rays from a distant star, and you see us attempting with a telescope to observe that star. And if there were no ether, or no motion of Earth relative to the ether, then observing that star would mean pointing the telescope right at the star. But because the Earth is moving on its orbit, as shown by the velocity vector here in this particular position pointing upward, the Earth is moving and there's ether, presumably, I have to point the telescope in such a way that the relative motion between Earth and ether and light brings the light into my telescope. That is, I have to point the telescope like that. It's a little bit like trying to walk or run through rain with an umbrella. Even if the rain is falling vertically, you have to tilt the umbrella to stay driest. And the same thing happens here. If the Earth is moving relative to the ether, is not dragging the ether with it, then we have to point the telescope in a different direction to the star. Now, that doesn't tell us much. But if we wait 6 months, that direction is different because now on this diagram, the Earth is moving downward as indicated by another velocity vector. So between times observations 6 months apart, we have two different directions to this star. The direction to the star, the apparent position of the star, seems to wobble over time. That's called the aberration of starlight. That phenomenon was first measured in 1729 by the English astronomer Bradley. On the left, you see some actual data listed in his paper. On the right, you see a graph I've actually made from reading that data off the table. And you see a kind of sinusoidal variation in the position of the star. It's a very subtle effect. But even by 1729, astronomers were able to measure that effect. So we rule out the possibility that Earth is at rest with respect to the ether. Earth must be moving relative to the ether. We know that from double star observations and from the aberration of starlight. Now we want to attempt to detect and measure that motion. We want to use Earth's orbital motion as the motion we're talking about, the changes in Earth's orbital motion over the seasons, to detect Earth's motion through the ether. If Earth is moving through the ether, as we have just found it must be, then there must be a wind of ether blowing past the Earth, and that wind is going to affect the speed of light in different directions as the Earth moves around in its orbit. So we should measure different speeds of light in different directions because of this ether wind that's blowing past the Earth. And the effect should vary over the years, so we should be able to detect this effect. And I'm going to spend the rest of this lecture looking in detail and getting quantitative about how we attempted to do that. The famous experiment that did that, the one that succeeded or didn't succeed, and then famously didn't succeed, was done after a number of other attempts failed, some of which were doomed to failure because they weren't measuring with mathematically enough precision, but the Michelson-Morley experiment was. The Michelson-Morley experiment consisted of sending light on two round-trip paths, one of them parallel to this ether wind and one of them perpendicular to the ether wind, and we were going to detect differences in travel time. Very subtle differences, but using very clever techniques. The first experiment Michelson did in 1881, and it wasn't really quite sensitive enough to achieve a measurement of the Earth's motion relative to the ether. But by 1887, he and his colleague Morley had made an experiment that was sensitive enough, and they performed it at what was then Western Reserve University, now Case Western Reserve in Cleveland, Ohio. They performed this definitive and very crucial experiment, and I want to spend a while describing that experiment. So let's go over to our big monitor where we do our mathematics, and let's begin looking in detail, in mathematical detail, at the Michelson-Morley experiment. So what I have here is a set of blue arrows that are indicating the direction of the ether wind. And you might say, well, we don't know what the direction of the ether wind is. It's okay. Don't worry about that. Let's suppose we can find that direction, and then we'll see why that doesn't matter a little bit later. And we measure a light path that is moving upstream against the ether wind. Now, the ether wind is blowing with some speed v. That's the speed of the Earth relative to the ether at the time we're doing this experiment. This light is struggling against that ether wind, and the light speed relative to the ether is c, the speed of light, because that's what the ether is. It's the medium in which light is a disturbance. So the light speed relative to the ether is slowing the light down because the ether wind is blowing against the light's motion, is c minus v. It's slowed down by the speed of the ether wind. Distance is speed times time, so time is distance divided by speed. So the upstream travel time for that light along its path is the length of the path, L, divided by the speed, c minus v. Now, what if we go downstream? Well, if we go downstream, the same thing happens, except now the ether wind is going with the light, and so the light is sped up. The speed of light relative to the Earth then becomes c plus v, and the downstream travel time becomes the distance, L, same distance, over this faster speed. By the way, you might have thought, well, these effects are going to cancel out because I'm going against the wind, going upstream, I'm going with the wind, going downstream. They'll cancel out. They won't cancel out, and the reason they won't cancel out, as you can see, those quantities are different, for one thing. The reason they won't cancel out is because you're spending more time fighting against the ether wind going upstream than you are going downstream, and so that makes an asymmetry that causes these effects not to cancel out, and there is a change in the time it takes for light on those two paths. So here are our results so far. The upstream travel time was the distance of the path, the length of the path, divided by the upstream speed fighting against the ether wind. The downstream travel time was the length of that path divided by this higher speed. We want to know the total travel time. The round-trip travel time is the sum of those two. Well, we're quantitative types in this course, so let's get quantitative. Let's look at that expression a little bit more. I've got two fractions I've got to add. How do you add fractions? You put them over a common denominator. Common denominator is the product of these two terms. That's, let's put this one over the common denominator, c minus v times c plus v. So I got a c plus v upstairs and a c plus v downstairs. I've just multiplied by 1 in the form c plus v over c plus v. This one I've multiplied by 1 in the form c minus v over c minus v, and I have that ugly-looking expression. But you may remember from high school algebra that when you multiply a plus b times a minus b, you get a squared minus b squared. If you don't remember that, just do it out. It takes you about 30 seconds, and you'll see that that's true. And upstairs we have an LC there, and an LV there, and an LC there, and a minus LV there. So there's some cancellation. The LVs go away, but we've got two LCs. And so there's our expression. And let me just simplify it a little bit. Let me factor the c squared out of the denominator here. That'll pull a c squared out in front, make that a 1, make that a v squared over c squared. And that c squared I pulled out is going to cancel the c upstairs. And my final result is 2l over c with downstairs this modifying factor 1 minus v squared over c squared. And that shows you, by the way, that the effect we're looking for depends not on v relative to c, the speed of the Earth through the ether relative to the speed of light, but the square And since the speed of light is big and these speeds are small, that's an even tinier quantity. It's a very difficult thing to measure. Now let's look for the light path perpendicular to the ether wind. Same path length L, but we're going to go up and down perpendicular to the wind. Well, to go on that parallel path, the light actually is going to have to go kind of upstream against the ether wind a little bit. So if we look at this, we can draw a vector diagram, and the vector diagram shows the speed of light relative to the ether is c. This is the velocity arrow for the light. The light is being pushed downstream by the ether wind at the same time, and so this vector represents the speed of the light relative to Earth. What is that? Well, we've got a Pythagorean triangle here. C is the hypotenuse, V is the short side squared plus long side squared equals c squared, or long side is c squared minus short side squared, take the square root to get the actual length. So the light speed relative to Earth in this case is square root of c squared minus v squared. And when we go back, we're still going to have to go at the same angle against the ether wind. And so on both legs of this trip, we have the same speed. And so the round trip travel time is the round trip distance 2L divided by that speed, 2L over c squared minus v squared square rooted. And I can factor out the c squared downstairs in the square root. When I take it out of the square root, it becomes unsquared. And I have that same 2L over c, and then I have a square root downstairs. And so what's the time difference? That's what we're trying to detect. The round trip travel times are the parallel path, up and back, the perpendicular path. They're different, and they differ in that one of them has the square root in it and one doesn't. And we could work this all out algebraically. I'm not going to do that, but I'm going to do the numbers. The orbital speed of Earth is about 30 kilometers a second. That's the minimum speed we could be moving relative to the ether. Maybe we're moving a lot faster, but that's the minimum. That's what we got to detect. C is 300,000 kilometers a second. L, for the Michelson-Morley experiment, the length of these paths was about 10 meters. We do the numbers. T parallel minus T perpendicular comes out. Tiny number, 3 times 10 to the minus 13 seconds. You're going to measure that in the 1800s? Yep, with clever techniques. So how do we do that? Let's talk about how we then measure this tiny, tiny time difference that we're talking about here. We do it with the Michelson-Morley experiment in its 1887 incarnation. Here's the experiment. On the left, you see a light source. Today, it would be a laser, but in those days, they had to use simpler light sources. In between, I have in the middle of this diagram a diagonal piece called a beam splitter. You can think of the beam splitter as just a mirror that doesn't have enough silver on it to reflect all the light. Half of it goes through, half of it reflects. An actual beam splitter is a more sophisticated device that uses total internal reflection, actually, but you could make one with a half-silvered mirror. At the extreme ends of this thing are 2 mirrors, just plain, ordinary, flat, reflective mirrors, and the path lengths, the light comes out of the light source, some of it goes through the half-silvered mirror, reflects off that far mirror, some of it reflects off the half-silvered mirror, reflects off the upper mirror. Those light beams return, and they join, and they go into a viewer. Now you might say, well, we got to really make this perfect in order to get those 2 light paths exactly equal. That turns out not to matter either, because we're only going to look at changes. So although I did the math as though the perpendicular and parallel path lengths were exactly the same, that doesn't matter. I also did the math as though we knew we were exactly perpendicular or parallel to the ether wind. That doesn't matter either, because we're going to rotate this whole apparatus around. So there are the returning beams, and they come join in this viewer. How do we possibly detect a time as short as 10 to the minus 13 seconds, especially in 1887 when we don't have high-speed digital counting devices and so on? Well, the answer is we be clever. And Michelson, whose biography is called The Master of Light, Michelson was a brilliant experimenter in optics, and particularly in something we looked at in Lecture 43, and that is the interference of light. He used light interference to be able to measure that very, very small time difference. So here comes the ether wind past our apparatus. The ether wind is going to change the time it takes to travel on those 2 light paths. And that means light that started out from the light source and then was split by the beam splitter and then traveled those 2 paths and came back together again. The light traveling one path has taken a little longer than the light traveling the other path, and so the light waves come in out of phase. And so there's some interference between them. Now, this picture is a little simplified in a way that makes it sound like it's going to be hard to detect that, but actually, I've drawn these paths perfectly parallel. Actually, the light coming out from the light source is going at slightly different angles, and there are rays of light going at very slightly different angles, so they're coming back together with slightly different interferences. Some interference is constructive, where crests and crests meet. Some is destructive, where crests and troughs meet. And so we get an interference pattern in that viewer in the 1887. Nowadays, we'd put a detector there, a digital detector, like in a digital camera. And we see an interference pattern. And this picture I've just dropped in is an actual picture from a Michelson-Morley experiment. And what you see are bright, dark, bright, dark, bright, dark fringes, the kind of thing you're used to seeing in interference of light. Those fringes are caused by places where light traveling those two paths comes back together out of phase by exactly one period of the light, or by one wavelength in distance. The dark are where they're out of phase by half a wavelength. That's how the Michelson-Morley experiment is going to detect the change in the period, or the change in the time for the two different light beams. And you might say again, well, how do we know what it should look like? We don't care what it should look like, because what we're going to do is rotate this apparatus. We don't really know it's lined up with the ether wind like I've shown here, but it doesn't matter, because we're going to rotate the apparatus. We're going to look at it in all different orientations. And the only thing we really care about is there a shift in the positions of the interference fringes? Because no matter where the ether wind is, and no matter how we're oriented relative to it, if we change our orientation, then we will change those interference patterns, and we will see a fringe shift. And Michelson and Morley knew how much fringe shift they were going to expect. There it is another time. Remember, I said it didn't matter whether we were parallel or perpendicular. If we try it in all these different orientations, we should see, as we rotate the apparatus, a shift in those fringes. Here is a picture, a drawing of the actual Michelson and Morley apparatus. It actually had multiple mirrors, and the light bounced back and forth a number of times and made for light paths that, as I said, were about 11 meters long, roughly 10 meters long, which I used in my calculation. The whole thing was on an enormous stone slab floating in liquid mercury. OSHA would never approve of this experiment today, because the room must have been full of mercury vapors. And the floating on liquid mercury, because a stone is less dense than mercury, so buoyancy, Archimedes' principle, it floats. You can easily rotate this whole massive stone slab on the liquid mercury. And here's what you expected. The expected result was a shift of 0.4 fringes. Now, how did I get that? Remember, I calculated that delta t, that time difference, as about 10 to the minus 13 seconds, 3 times 10 to the minus 13 seconds. That turns out to be about a fifth of the period of visible light waves. So 3 times 10 to the minus 13 seconds, it's a fifth of the period, the oscillation period of visible light waves. They're oscillating 10 to the 14, 10 to the 15 times a second, very fast. The period of the visible light, the time between one cycle and the next, or the distance between one cycle and the next, the wavelengths, is represented by the distance between the center of one of these bright fringes and the center of the next bright fringe. So that's a fifth. We're trying to detect a shift of a fifth of that whole distance, or 2/5, 0.4, of a full fringe, of one of those bright fringes. So the diagram shows you roughly what we should have expected. In one orientation of the Michelson-Morley experiment, we should have seen the fringe in the upper position. In the lower position, we're looking at the orientation when we've flipped the apparatus 180 degrees or 90 degrees relative to the ether wind. And again, we're not really looking for just two orientations. We're rotating this apparatus on its liquid mercury bed, and as that happens, we should see these fringes shift back and forth, and the extreme shift should be 0.4 fringes. So that's what we should expect. And despite the fact that we didn't have any clocks or anything capable of measuring such a tiny distance or such a tiny time, you can see that we could, with careful measurements, detect this difference that I've shown you here. So what actually happens in the Michelson-Morley experiment? We expected a shift of 0.4 fringes. Michelson and Morley, good scientists they were, didn't say we didn't find any shift, but they said if there was a shift, all we can say is the upper limit to it was 0.005 fringes. Essentially no shift, no result, no measurement, failure of experiment. One of the most famous failures in all of physics. And here's how they summed it up in their paper. The interpretation of these results is that there is no displacement of the interference bands. More verbiage. Ending with the statement that the hypothesis of a stationary ether is thus shown to be incorrect. The Michelson-Morley experiment shows that the Earth's motion relative to the ether is not detectable. We don't have a stationary ether relative to the Earth. We knew that. We don't have Earth moving relative to the ether. We haven't been able to detect the Earth moving relative to the ether. The Michelson-Morley result fails to detect the Earth's motion through the ether. What are we to do about this? We had to have this ether, first of all, to give this mechanical interpretation of electromagnetism. More significantly, we ended up having to have this ether because the aberration of starlight and the double star systems tell us that light does not move at speed c relative to its source, and that the Earth is not at rest with respect to the ether. So where do things stand now in physics? Here we are in 1887. We've got this problem in that there is seeming contradiction in physics. The Earth is not at rest with respect to the ether, but we can't detect Earth's motion with respect to the ether. We also have a dichotomy, a philosophical dichotomy that I haven't mentioned before. Remember that in Newtonian physics, all that matters is the change in motion. There's no preferred reference frame for Newtonian physics. I can be on a cruise ship playing tennis in an indoor tennis court, and the fact that the ship is moving through the ocean at 30 miles an hour has no impact on my game. Newtonian mechanics works perfectly in any moving frame of reference. You can eat the little airline peanuts that they used to give you on airplanes without worrying about the fact that the airplane is rushing along at 600 miles an hour. Newtonian physics works in any reference frame. But, at least in this mechanical view of 19th century physicists, electromagnetism has a preferred reference frame. It's the reference frame at rest relative to the ether. And yet, we can't detect the reference frame relative to the ether. So this leaves us a real contradiction in physics. First, a real contradiction in that we're supposed to be able to detect that motion. We can't detect it. And then this kind of philosophical dichotomy that one branch of physics, mechanics, has no preferred reference frame, and the other branch of physics, electromagnetism, seems to have a preferred reference frame, but we can't find that reference frame. Well, there were clever physicists thinking about this, and there were a number of kind of ad hoc hypotheses proposed. The most significant one was the so-called Lorentz-Fitzgerald contraction hypothesis, proposed independently by the Irish physicist Fitzgerald and the Dutch physicist Lorentz. And they proposed that when objects were moving through the ether, they got compressed in the direction of motion. You can kind of imagine that might happen. This ether wind is pushing on the object. And they got compressed in just such an amount to make to shrink the path along and against the ether wind and make the times be the same on the two paths, and so you could not detect motion through the ether with an experiment like Michelson-Morley because of this contraction effect. Now, there turns out to be a grain of truth in the Lorentz-Fitzgerald contraction, which we'll get to in the next lecture. But that grain of truth is based on a very ad hoc assumption, and it clings to the idea that there is this mysterious and problematic substance, the ether, going through the entire universe. We'll see later how we get rid of that. Let's wrap up this lecture. We began thinking about Earth, ether, and light. We wanted to have a mechanical view of light and all other electromagnetic phenomena. The ether is the medium for light and other electromagnetic waves, and indeed for electric and magnetic fields. So we've got this mechanical view we want to kind of stick with. But binary star observations show us that light doesn't depend on the speed of its source, and therefore if we wanted to get rid of this ether, if we wanted to throw over this mechanical view, then we would have to come up with another answer to the question, with respect to what does light go at speed c? The aberration of starlight shows us that the Earth is not at rest with respect to the ether, and therefore we have to be able to detect Earth's motion through the ether. The experiment that does that is the Michelson-Morley experiment. The ether wind should make the speed of light direction dependent. The experiment uses wave interference. It's very sensitive, and it fails. The Earth is not moving relative to the ether, and we're left with a big, huge contradiction in physics. Okay, before we end, though, let me move you on to a little challenge, since we are quantitative here. I'd like you to go back to the mathematics, where I looked at the perpendicular round-trip travel time and the parallel round-trip travel time, and I would like you to show mathematically that as long as the speed of the ether of the ether wind, or the speed of the Earth relative to the ether, is less than the speed of light, then the perpendicular round-trip travel time is always less than the parallel, anti-parallel round-trip travel time. How do you do that? Well, we had those two travel times, the one that had the square root in it, the one that didn't have the square root in it, and I'm asking you to show that one of them is bigger than the other. So let's multiply by c and take c inside the square root there, sort of going back from what we did. And now we have an expression that looks like that, t parallel minus t perpendicular. Put them over a common denominator, c squared minus v squared. This time the square root goes in, and we get a square root upstairs on the second case. And if we work on that just a little bit, pull out the 2LC, we've got 2LC, 1 minus the square root of 1 minus v squared over c squared. That number is going to come up again and again, and it's over c squared minus v squared. And I've said v is less than c. And what that means is the quantity in the square root is less than 1. The quantity in the denominator is less than c, but both those quantities are positive. The numerator is positive. The denominator is positive. The answer is a positive number, and that shows us that the parallel path takes longer than the perpendicular path, and we've proved it.